Hello everyone. This video is on the Knewton Alta assignment for section 5.3 part 1 called Local Behavior of Polynomial Functions. So in this video I'm going to be going over a preview version of this particular assignment. So please understand that the questions I see in this video may not be the same questions that you see when you work on the assignment yourself. But the objectives are all the same, so I'm hoping that the questions are similar enough so that watching me do a few will help you out in some way when you work on the assignment yourself. Alright, so on your assignment page, you should see the title, you have your mastery bar, look at the objectives. Looks like there are 3 objectives in kind of 2 different sections here. And under the current objective, you should see a question related to that objective. And at the bottom of every question, you should see a feedback button. You can send feedback to Knewton. You will not have this instructor cheat button. It's for instructors only. But you will have a more instruction button. Right, if you're struggling with a topic, click on this. It'll take you to a page with some reading or some videos and give you questions related to the instruction, and you can get through the assignment that way if you wish. Alright, so this first objective is identify if a graph is, the graph of a polynomial function. Alright, so before I get to this question here, I want to talk about, what are some characteristics of the graph of a polynomial function? Alright, so hopefully you recall from earlier sections, either 5.1 or 5.2, that a polynomial function is any function that can take this form, f of x equals y equals, and then you have some number, a sub n here, times x to the nth power, where the powers on the variables are whole numbers. Right, and this continues on all the way down to some number times x to the first plus some constant. Right? And a polynomial can have one term, it can have 2 terms, many terms. Right? And again, all the exponents are whole numbers. All the powers on the variables are whole numbers, right? 0, 1, 2, 3, and so on. Now, for the graphs, and you've seen a few graphs of polynomial functions in previous sections. The graphs of polynomial functions are continuous. On the entire real number line. So everything from negative infinity to infinity. What that means is, you can basically draw the graph, going from left to right without lifting your pencil, right? Without lifting your pen. There's no holes in the graph, no break in the graph, nothing like that. Right? And it's, you can plug in any value of x and get a value of y, and it's all connected. There's no breaks, no pieces. So that's one. Another thing about graphs of polynomial functions is that they are what they call smooth everywhere. Now, smooth just means that there's no sudden turns, no sharp turns. Okay, so you're not going to see stuff like this. Right? You're not going to see a sudden, there's no pointy places, like a turn and then sharp turn, stuff like that. You're not going to see any of that. So like again, back in this graph over here, this could be the graph of a polynomial function. Very smooth, right? What you will see are smooth curves, right? So like something like this could be the graph of a polynomial function. The turning points are at very rounded turns, right? No pointy turns. Okay, I hope that makes sense. And then on the ends, the graph is going to either go to infinity or negative infinity. And we've talked about this in some previous sections, section 5.2, on the end behavior of a polynomial. But on the ends, the graph is going either up forever or down forever. The graph value either goes to infinity or negative infinity. Right? So like these graphs here, on the right end it's going to infinity. On the left end the output's going to negative infinity. If I had some axes in here, right, x, y axis, on the right end, going to negative infinity, left end going to negative infinity. There aren't going to be what they call horizontal asymptotes. The graph's not going to approach, 3, get closer to 3 on the end. It's going to go to infinity or negative infinity and not some specific value. Okay, so no asymptotes, no sharp turns, no holes, no breaks. Very smooth, continuous, and then going either up forever or down forever on the ends. Right? Those are the graphs. Those graphs like that are graphs of polynomial functions. Okay, so back on this first question, they ask us, which of the following shows the graph of a polynomial function? And select all correct answers, right? So there's maybe more than one choice here. All right, so you see this first function. Yes, it is continuous. Yes, it is smooth. But, see on the left end and the right end, the graph's not going up forever or down forever, right? It's not approaching infinity or negative infinity. It's approaching some finite value. That does not happen in the graph of a polynomial function. So yes, it's continuous and smooth, but the end behavior tells me that this is not a polynomial function. Okay, same thing here. Yes, it is continuous and smooth. No pointy places. But in the right end behavior, the graph looks like it's going to negative infinity. But on the left end, it looks like it's approaching some horizontal line, right? It looks like it's approaching some finite value, not going up forever or down forever. Now, it may be going up forever very, very slowly, but it just based on first glance, it doesn't look like it's the graph of a polynomial function because it doesn't look like it's approaching positive infinity on the left end here. It's approaching some horizontal line, some finite value. So again, based on that end behavior, I would say that this is not the function, not a polynomial function. All right, now this one, continuous, smooth, right? The curve is nice and rounded. And it's going up forever on both ends, going to infinity on both ends. That's fine. So I would say that this could be the graph of a polynomial function. So I'll select it. Next one, same thing. It's continuous, it's smooth, right? There's no holes in the graph, no breaks in it. The curves are nice and rounded. There's no sharp turns. It's smooth. and the end behavior is like that of a polynomial function. It's either going to infinity or negative infinity, right? It's going to infinity on both ends. So this could also be the graph of a polynomial function. So I'll click that one. All right, and this last one is definitely not the graph of a polynomial function because it's not continuous. You see here you have a vertical asymptote at -4. Right? The graph, there's a break in it. You can't draw it from left to right without lifting your pencil. So not clicking that one. Alright, then after you submit an answer, it'll tell you if you got it right or wrong, and then it'll provide you, it should, with some answer explanations. Please read through the answer explanations just to make sure you understand why something was right or wrong, and maybe you can learn from your mistakes for the future. Okay, next question. So same objective, same kind of question. Which of the following shows the graph of a polynomial function? So we got continuous, smooth, right? No sharp corners. And there's no horizontal or vertical asymptotes, right? The graph is approaching infinity or negative infinity. In fact, it's approaching negative infinity on both ends. This could be the graph of a polynomial function. This one is continuous, right? There's no holes in it, no breaks, but it's not smooth. You see this pointy place here, this pointy turn. So this is not going to be the graph of a polynomial function. This isn't continuous, right? At x equals 1, there's a vertical asymptote. Graph has a break in it, so definitely not the graph of a polynomial function. This one could be continuous, smooth, and approaching infinity or negative infinity on either end, right? No horizontal asymptotes, so click that one. And then this one is continuous and smooth, but it looks like it has what they call, again, a horizontal asymptote. The graph is approaching some horizontal line on the ends and not infinity or negative infinity, so not the graph of a polynomial function. Pardon me. Great. And I think it's going to continue with this objective until until it's done, and then we'll move to the other two. So once again, identify the graph of a now this one has a horizontal asymptote, approaches some horizontal line on the end, so that can't be a polynomial function. Same thing with this one. This is continuous, smooth, and has no asymptotes. Goes to infinity or negative infinity on either end. So yes. Right. Now it might look like the y-axis is an asymptote, but I think it's touching here and continuing down forever to the right. So I'll say that one's a polynomial function. Same thing here. It's continuous, it's smooth, goes to negative infinity on both ends. And this one's continuous but not smooth again, right? You got that sharp corner, sharp turn. So that can't be a polynomial function. Pardon me again. Alright, there should just be one more like this. So here again, not smooth, right? Sharp corner. This looks good. Continuous, smooth, no asymptotes. This has a horizontal asymptote, right? The graph is approaching some horizontal line on the end, so no good there. This is good. This could be a polynomial function, right? Continuous, smooth, no asymptotes. This has a horizontal asymptote. The graph is approaching some horizontal line on the left end, so not going to be a polynomial function. Alright, great. So that, hopefully those three things that you're looking out for, is it continuous? Does it have any holes or breaks? Is it smooth, right? Does it have any sharp corners or not? And Does it have horizontal asymptotes or vertical asymptotes? Does it approach infinity or negative infinity on the ends? Those are the three things you're looking out for when you're saying, could a graph possibly be a graph of a polynomial function? All right, so now we're moving to the other two objectives. Now, the next objective is understand the relationship between degree, turning points, and x-intercepts. Right. So let me talk about that real quick. So keeping the whole polynomial up here, sorry. Remember, the degree is just the highest power. So like of all this would be the the nth degree. It's the exponent on the variable in the highest powered term, the leading term. All right, and if the degree is n, then the graph will have at most, okay, so no more than n minus 1 turning points Now, turning points are the tops of hills and bottoms of valleys. Right. Turning points are, this point here and this point here, the top of a hill, the bottom of a valley, the bottom of a dip. Turning points are, where the graph goes from increasing to decreasing, or from decreasing to increasing as you go from left to right. So a degree n polynomial can have at most n minus 1 turning points, and at most n x-intercepts. It can't have more than n x-intercepts. And remember, x-intercepts when you're graphing are just points on the x-axis. So like this point here. So again, if it's a degree n polynomial, it won't have more than n x-intercepts, and it won't have more than n minus 1 turning points. So keep that in mind. That's all you need to really know for this objective, I believe. So for instance here, right, given that the degree of the polynomial f of x is 7, which of the following most accurately describes the number of x-intercepts that f of x has? So if f has degree 7, it can't have more than 7 x-intercepts. So it has at most 7 x-intercepts, and that's this statement here. And that's all. That's all. It can't hit the x-axis more than 7 times. Very, very simple. It's the same objective, talking about turning points. So given that polynomial has degree 8, which of the following most accurately describes the number of turning points of that polynomial? Right? If you were to graph how many turning points could it possibly have? And I mentioned this on the page, right? If a polynomial has degree n, the graph will have at most n minus 1 less turning points. So a degree 8 polynomial can't have more than 7 turning points. So that's this first statement, right? The graph has at most 7 turning points. And that's it. That's all they're asking. All right, so now the other objective is identify the intercepts of a polynomial in factored form. So find the x-intercepts and y-intercepts. Well, that's that. If it's in factored form, should be very, very simple, and I'll show you. So I'll write out the function they gave us, and, where it's not completely factored, but it is nice and factored down to linear factors, degree 1 factors already. We have f of x equals x plus 2 times x plus 4 times 2x plus 10. And they're saying find the intercepts. Now, remember the y-intercept is simple. Remember, to find the point of the graph on the y-axis, you set x to be 0, right, the input. So what is f of 0? I'll just replace all the x's with 0, right? That would be 0 plus 2 times 0 plus 4 times 2 times 0 plus 10. And we end up with just 2 times 4 times 10. Right, 2 times 4, and this would be 10. And that's 80. Right, input 0, output 80. So the point 0, comma 80 is what they're looking for the y-intercept. And then again, you've done this before, I'm sure, right? For x-intercepts, you set the output to be 0. Set f of x equal to 0. So basically we're solving this equation. When is f of x? When is x plus 2 times x plus 4 times 2x plus 10 equal to 0. And then we can, since this is in factored form already, we can use that zero product property. Right? When a product equals 0, one of these factors has to be 0. You hopefully recall this from when we were solving, quadratic equations by factoring. Right? Once you have a factored polynomial on one side, 0 on the other, then one of the factors has to be 0. So either x plus 2 equals 0, or the next factor, x plus 4 equals 0, or this third factor could be 0 as well, and the statement would still be true. 2x plus 10 equals 0. And then we solve each of these. Now here, subtract 2 from both sides, x equals negative 2. Here, subtract 4, x equals negative 4. Here, I'd subtract 10, but then have to divide by 2, right? Negative 10 divided by 2 would be negative 5. And there are, the 3 x values for the x-intercepts. So the x-intercepts would be, negative 2, comma 0, right? Input negative 2, output 0. Negative 4, comma 0, right? Input negative 4, output 0. And negative 5, comma 0. If you were to input negative 5, the output would be 0. And, there we go. That's what they want. They want these x-intercepts and y-intercept. And then, like I said, you've done this stuff before with the zero product property and whatnot, finding intercepts of graphs. So this shouldn't be too terribly difficult, especially if the polynomial is given to you factored already. Alright, so one of the x-intercepts, now they put the parentheses there, they just didn't put the commas, right? So one of them is at negative 2, comma 0, and then I go over to the next box, the parentheses are already there, so I'm just entering the coordinates, negative 4, comma 0, and then, the next box, negative 5, comma 0, and the next box, the y-intercept was 0, 80, right? The coordinates were 0, comma 80, right? Okay, and that should be good. Wonderful. And they even show you the graph. And you can look at the graph on Desmos. I mean, I do have Desmos here, but I I don't feel the need to do that. You know, they show you that right here. The 3 x-intercepts, the y-intercept. Okay. Alright, so we're sticking with this. Now, again, already factored. I'm going to just speak what I'm not even going to write these out anymore. Right? The y-intercept, you know, if you were to replace x with 0, you'd have 7 times 1 times negative 2. The output would be negative 14. So the y-intercept is 0, comma, negative 14. And then the x-intercepts, you know, if f of x were replaced with 0 and you applied the 0 product property, you know, you solve the equation where you set everything equal to 0. Either x plus 7 is 0, or x plus 1 is 0, or x minus 2 is 0. Well, when x plus 7 is 0, x would be negative 7, right? So negative 7 comma 0 is one of the x-intercepts. When x plus 1 is 0, that means x is negative 1, so negative 1 comma 0 would be another x-intercept. And when x minus 2 is 0, yeah, x equals positive 2, right? So 2 comma 0 is the third x-intercept here. And it's really that simple. I mean, you shouldn't have to do too much writing if you're doing any writing at all for these. And once again, I think they'll show you the graph, you know, see the y-intercept, see the 3 x-intercepts. Great. All right, one more of these. So again, what's the y-intercept? Plug in 0 for x. So then these will become negative 5 times negative 3. That's 15, positive 15. And then if x were 0, this last value of the value of this last factor would be 8. 15 times 8 is, you know, 120. So 0 for x, comma, 120 for y. That's your y-intercept. Then the first, you know, and again, we're just setting this product equal to 0 to find the x-intercepts, right? You set the output, set f of x to be 0. X minus 5 is 0 when x is 5, so 5 comma 0 would be an x-intercept. X minus 3 is 0 when x is 3, so 3 comma 0 would be another x-intercept. And 4x plus 8 would be 0 when x is negative 2, right? You'd subtract 8, divide by 4. So negative 2 comma 0 for the third x-intercept there, and that's it. Very, again, in my opinion, pretty easy. If it's already, if the polynomial is already factored for you, this should be pretty simple. And once again, they show you the graph where you can see all the intercepts. Great. All right, they have 4 of these in a row. Okay. So once again, y-intercept, plug in 0 for x. Then you'll have negative 5 times 1, so negative 5 still, but then times 15. Right, so negative 75 for the output when the input is 0. So 0, comma, negative 75 for the y-intercept. And then the x-intercepts are even easier, right? You're setting this whole thing equal to 0, right? When is the output 0? And then apply that 0 product property. X minus 5 is 0 when x is 5. So 5 comma 0, 5, 0 would be a x-intercept. X plus 1 is 0 when x is negative 1, right? So negative 1 comma 0 would be another x-intercept. And then finally, this third factor, 5x plus 15 would be 0 when x is negative 3. And you'd subtract 15, then divide by 5. So negative 3 comma 0. And again, that should be it. Wonderful. All right, so when the polynomial is already factored for you, finding the intercepts should be simple. All right, then we're back to that. Just remember the relationship between degree, turning points, and x-intercepts. once again, if the degree is n, a polynomial will have at most n x-intercepts and at most n minus 1 turning points, right? Those tops of hills or bottoms of valleys. That's all you need to remember. So here this polynomial they're telling us now this has 7 x-intercepts. Which of the following most accurately describes the degree? So if it has 7 x-intercepts, it has to have degree 7 or more. Right? It could be degree 7, degree 8, degree 9, but if it has 7 x-intercepts, it can't be degree 6 or 5 or 4, anything less than 7. So if it has 7 x-intercepts, it has to have a degree of 7 or more. So at least 7 is the degree of f. That's the statement here. All right, I should have one final question in this objective. All right, so this says, the polynomial has 5 turning points. So those, those tops of hills or bottoms of valleys. Which of the following most accurately describes the degree of f? Now remember, if it has 5 turning points, the lowest degree f could be is 6. Right? Because remember, a degree 6 polynomial will have at most 5 turning points, n minus 1. Right? So the polynomial has to be degree 6 at least. Right? It could be degree 6 or 7 or 8 or 9 or 10 or whatever. All those could have 5 turning points. But it can't be degree 5, it can't be degree 4, 3, 2, 1, 0. Right, so it has to be degree 6 or more. Right, at least 6. So that statement I just highlighted there. And great. So again, pretty easy, quick concept in my opinion, but hopefully those are simple. All right, and that's it. That should be it for this preview version of this assignment. As I said at the top of the video, please understand that the questions I see here may not be the same questions that you see when you work on the assignment yourself, but the objectives are the same. Right? So the questions should be similar enough so that watching me do some here hopefully help you out in some way when you work on the assignment on your own. And thank you very much for watching.